Okay, so just before I start, thanks again to the conference organizers for hosting this amazing conference. It's been really, really great. And yes, I'm going to be talking about the Dragonfly Spectral Line Mapper and our recent efforts to finish construction and start our survey of mapping the CGM of local galaxies. So just before I get started, I just want to shout out to Bob Abraham and Peter Van Dockum, who are profs at U of T and Yale, as well as Siri Chen and Ahmad Pasha, who are grad students who have done a ton of work towards this project. So before I get started, I wanted to talk a little bit about mission line studies, because we haven't really talked about that field yet, but it is a really great recent field that's kind of come to fruition in the last decade or two for doing this two-dimensional mapping of the circumgalactic medium. And it used to be that mission mapping was only possible through stacking, but with the advent of new instruments such as KTWI on Keck and Muon BLT, astronomers have actually been able to directly detect the circumgalactic medium. So this is an example of one of the first direct detections of basically a Lyman alpha map of emission, kind of lunar emission around a higher redshift quasar. And so since then, there's been a lot of amazing data coming out, mapping the CGM of these what I'm going to call high redshift galaxies and quasars mainly. And I'm just going to show some examples here. Like there's a lot of data coming out, so I'd encourage you to check this stuff out. So, and not just the CGM, but also filamentary emission now is starting to be detected. And this is possible mainly due to these bright UV lines that are accessible at high redshift, such as Lyman alpha, magnesium 2, which means that there has been a gap in the local universe where you have basically you can't access these UV emission lines from the ground. So it's very difficult to map the CGM because there's just nothing bright enough that you can go and target with your galaxies. And also the scales of the CGM in the local universe are not as well suited to our current facilities. So if you can make it out there, I've shown the fields of view of some of these IFU instruments on top of like a local galaxy. I think that's the Whale Galaxy. And you can see that their fields of view are quite small compared to the CGM. So I've shown also in red some like narrow band imager scales. So this larger field of view can be much more efficient as a survey mapper when we're looking at these local galaxies. But of course it's very hard to do because once again we don't have access to those bright UV lines. And also our typical narrowband imagers, they are not well suited to detecting this ultra low surface brightness emission. And in fact, by looking at simulations, we need not just narrowband passes, but ultra narrowband passes to actually get enough signal to noise to make one of these maps of the circumgalactic medium in the local universe by looking at a line like H alpha or nitrogen or oxygen, like N2. And that's what brings me to talking about the Dragonfly Spectral Line Mapper. So this is a telescope I've been working on for the past few years. I've been designing and then building it. So we recently finished construction, and it's a different type of telescope. As you can see, it's modeled off of the Dragonfly telephoto array. And the main component of this telescope is actually Canon telephoto lenses, which reduce light scattering in the optics to enable ultra-low surface brightness imaging. In addition to this specialized imaging for low surface brightnesses, specialized optics for low surface brightness imaging, the Mosaic design also allows us to do another thing, which is important, which is to put our filters, our ultra-narrowband filters, in front of the optics. And this is very important because narrowband filters are interference filters, and that means that they have a dependence on the angle of incidence of incoming light. So if you stick them behind all your optics in a converging beam, you degrade your band pass. And I'll show basically an example of that in a second. But what we can do here is we can not only put the filters in front of our optics, we're in their completed beam coming from space, but we can also turn that bug into a feature by tilting the filters to scan through different wavelengths. So we make, even though we have this very narrow band pass, which we're aiming to be less than a nanometer wide, we can recover a larger wavelength range by tilting the filters. Okay, and so the takeaway, we can tilt the filters, which allows us to look at different wavelengths of light, which means we can target different emission lines and different redshifts of galaxies. Here I've just shown what we have shown both from theory and from instrumental effects, or instrumental measurements. Basically, if you have your filter at 0 degrees, the red line is the filter transmission profile, and you can see once we tilt it by 10 degrees, it smoothly shifts. The blue dashed line is what the filter transmission profile would be if we put that filter behind all the optics. So you can see it's not ideal, which is why we put it in front of our optics. And so just an example, we can not only look at different redshifts with the same filters, we can also use our tilting feature as a bit of an IFU to look at the different velocities within the galaxies themselves. So this is just an example from raw data, actually, just 3 exposures showing us tilting through the rotation curve of NGC 7331. So just some quick facts about the telescope. As I mentioned already, the main instrument that the baseline of the telescope is the Canon telephoto lenses, which you can just buy off the shelf. You can make your own Dragonfly if you wanted to. We also, for this one, we use CCD cameras, and we have these ultra-narrow bandpass filters. So in the Dragonfly Spectral line mapper, it's an expansion onto the Dragonfly telephoto array with the narrowband imaging capability, and we have 120 units, so 120 of these lenses split between 4 mounts. Each one has a filter. So we have, you can see here, we have 60 filters that can target the H-alpha or N2 line, and 40 that can target the O3 emission line. And the idea is we just put them each on one of the units, and then we go and look at this. Each unit, we point all the mounts at the same place in the sky, we take images, and we stack all our data to make a deep image. In addition to this, we have a whole bunch of off-band filters for calibration, sky subtraction, etc., which is the largest systematic in our data. And just some quick facts here. So just a reminder, we're looking at very low redshift galaxies, so local. So redshift less than about 0.01, which corresponds to going out to a radial velocity of about 4,000 kilometers per second. And what we've determined from Pathfinder imaging and from theory is that we should reach a surface brightness limit of about 10 to the minus 20 ergs per second. And yes, large field of view, as I already mentioned. So this is just a quick shot. So this is where the instrument is located. It's currently in New Mexico Skies Observatory. So we have 4 mounts built, and this is in addition to the Dragonfly telephoto array. I'm just going to really quickly touch on our Pathfinder results, just to remind people, because I've talked about this to this group before, but basically we went and looked at the very popular group of galaxies, the M81 group of galaxies. I'm showing here our broadband Dragonfly imaging on the left, and then the H1 map, beautiful H1 map in the middle that we saw yesterday. And this is our H-alpha map from just a small Pathfinder. And the main discovery in this space was this large shell of H-alpha and N2 emission in the outskirts of the M82 galaxy. So I'm just going to quickly go through this, but this was about 100 hours of observations with the Pathfinder, and we reached about 5 times 10 to the minus 19 in the surface brightness limit. For reference, this was the previous largest field of view image of M82. So you can just see the scale that we're trying to explore here. It's this very large scale to look at the CGM. Just some quick facts about the H-alpha shell, as we called it. It seems to be very low mass, and we're not sure exactly what's happening here. We did confirm it with spectroscopic data, which I'm showing here. And it does have some evidence for shock ionization along the inner edge there, which we think could be shock ionization from the M82 superwind. But anyway, happy to talk more about that, but we're excited to have more data like this. Right now, our surveys and data reduction are ongoing, so this is just very rough data just to show you that we have some data, but it's not really ready to share yet, so no spoilers. And that's not all. We're actually starting a whole new expansion to the Dragonfly Spectral Line Mapper, which basically was prompted by this one line back from our 2019 paper, which is that detecting each alpha emission from the diffuse intergalactic medium may be possible, would be possible, I said, with a hypothetical 1,000 lens Dragonfly array. And so, because of this, we are now just starting our new venture, Mothra TM, which will be an 1,026 unit version if we get the funding, which should happen by the end of the week. So fingers crossed. So that's what we're moving into, and yeah, happy to answer more questions about that too. But I figured I'd wrap up there at both of you. Thanks.
Any questions?
So you mentioned that by tilting the filter, you can almost get like an IFU. What, like, how precise is the tilt to, like, what would the resolution of such an IFU be?
Yeah, so our filter band passes are 8 angstroms wide, which corresponds to about 350 kilometers per second. So I guess you can consider that as like a very conservative velocity resolution, but we can actually micro tilt those filters and shift them by like 0.1 degrees, which corresponds to about like 0.1, by about 1 angstrom. And so we actually get a bit finer velocity resolution than that, so about like 50 to 100 kilometers per second. And so that's our, yeah, so that's what we have shown we can do right now. Yeah, it definitely relies on a good calibration or a lot of data so that we can then model it out later and make sure that we know what we're looking at. But yeah, that's our goal, is to look at that.
Yeah.
Nice thought. So what's the criteria of the sample selections in this manufacturing?
Yeah, that's a great question. So our current criteria is we're just looking at starbursting galaxies in the local universe with some slight focus on edge-on galaxies. So to be honest, we have a couple, those 2 grad students in Mod and Siri I mentioned, who just need to get some papers out. So we're going to go after what we figure are the low-hanging fruit right now. But once we start our actual survey, we'll be paying more attention to our survey selection. And what we'll be aiming for is an unbiased sample as much as we can make that. So we can go out to about like 40 megaparsecs. So we'll just be looking through the catalog to try and sample a whole range of galaxies and environments, etc. But if you have any suggestions, feel free to let me know.
We can do one more question, and Michael, if you want to come up and get set up. Is there one last question? Yeah.
Do you have any plans to look at any of the nearby galaxies and clusters, like Virgo or Fornax, that are obviously well within 40 megaparsecs?
Yes, we have planned a Virgo galaxy, galaxy cluster survey, and we have like a few targets in there that we are going to look at. So yeah.
Let's thank our speaker again.